This session introduces more utility methods on lists. You'll find out what these methods do and where they're useful, and you'll also learn how they're implemented in terms of the fundamental operations on lists and pattern matching. So in this session, you're going to find out about more methods that are useful for list processing. First one is the length method, so that gives you the number of elements that are in the list. You know already about head and tail, so if you have a list that I'm now writing as essentially a contiguous sequence of elements, then head would be the first one here, and tail would be the rest. The duals of head and tail are called init and last. So last would give you the last element in a list, and init would give you all elements except for the last. Then there's also take and drop. So take takes an arbitrary prefix of elements in the list, whereas drop would give you back all the elements in the list except for some prefix. So it would drop a number of elements from the beginning and then give you back the remainder of the list. And finally, we can also select into a list that's written xs of n, where n is an index, and that's expanded as usual to a call of the apply method of lists. So alternatively, we could also write xs apply n, they're the same thing, and that would give you back the element of xs at index n, where as usual indices are numbered from 0. Here are some more utility methods for lists. You might be interested in new ways to create lists. The first method here is concatenation. It's written xs ++ ys, and that gives you the list that consists of all elements of xs followed by all elements of ys. Then there's reverse, which, as the name says, will give you a list that contains the elements of xs in reversed order. And finally there's updated. So updated is in a sense the functional equivalent of mutable updates in an array when you change an element in an array. Of course, you know you can't do that in a list because lists are immutable. But what you can do is you can return a list that contains all the elements of the list xs here, except at a given index n, where the new list would contain the x. So it's a new list that corresponds to the old list xs in all elements except one. Besides creating, there are also two functions for finding elements. There's index of, which is very much like index of on, let's say, a Java string. So it tries to find an element x in a list xs and would give you back its index of the first occurrence of x if it's found in the list, and -1 if x does not appear in the list. And then there's contains. So xs contains x asks whether the element x appears in the list xs at all. So it's the same as xs index of x greater or equal to 0. Now let's look a little bit more at the implementation issues. We know that the complexity of head is a simple field selection, so it's a very small constant time. Can last be implemented just as efficiently? Tail again is just a simple selection of the second field of a list, constant time. Can init be implemented at the same efficiency? Well, let's see first how we would implement last. As I said, last is a method in class list, but to study its implementation we might as well define it as an external function outside the list class. If we do that, then last would have this signature that you see here. So it takes a list of t for an arbitrary type t and gives you back a t, the element type of the list, and the usual implementation of last would be to say, well, let's see what the list is. Last of an empty list should give you an error, just like head of an empty list gives you an error. Last of a list that contains a single element would give you just that element. And finally, last of a list that consists of a head followed by some tail would give you the last element of the tail. So we see by looking at this implementation that last takes a number of steps that's proportional to the length of xs. We need to take one recursion for each element in the list here. Let's do the same as an exercise with init. So I've given you another outline of an external function init, analogous to last. It takes a list of t for arbitrary t, returns a list of t. It's not defined of list of empty. So all you need to do is fill in the triple question marks for the two patterns. What happens if the list consists of one element, and what happens in the case where the list is a general first element y followed by a list ys. So let's see how we would solve this. The initial part of a list that consists of a single element would be the empty list. So we would return list of empty. The initial part of a list that consists of a head y and some tail ys, what would that be? Well, it would certainly contain the head, and then we would have a recursive call to init ys. So one thing that I've just not yet said explicitly here, but which is important, is that the patterns are actually matched in sequence. So what this pattern would match is any list of a single element. What this pattern then would match is any list of length 2 or more, because we have already covered lists of 0 and 1 elements. So that means that the recursive call to init on that list cannot fail, because we know that the size of ys is at least 1. So let's look at another fundamental operation on lists, concatenation. How is concatenation implemented? Well, you'll remember that if we write xs and then the triple colon for concatenation ys, that really is the same as the call of the method triple colon with receiver ys and xs as the argument. So it's a prepend of xs on top of the right hand side ys. Very much like the prepend function that you've implemented last week, but now you prepend a whole list, not just a single element. To find out how the implementation of that can be done, it's actually just as good to write a standalone function. I've given you the signature of concat here, so that would be a function that concatenates xs and ys, like you see here. How could that be implemented? Well, so far everything we did was by a pattern match on the list in question. But now there are two lists we deal with, xs and ys. So what list should we pattern match on? Well, the other observation is that once we were done with pattern matching, typically we constructed lists from left to right. We were asking the question, what is the first element of the result list and what is the remainder? Now, the first element of the result list, does that depend on xs or on ys? Well, clearly it depends on xs. So it makes sense to pattern match on xs. So let's do that. We have the standard match on xs, the empty case, and a case where the list is non-empty with a head z and a tail zs. Ys is already taken as a name here. So for the empty list, what should concat return? Well, obviously the empty list concatenated with some list ys is the list ys. So that would be our result. If the list is not empty, so it contains a head z and a tail zs, the next question is, well, what is the first element of the result list? Well, it's the first element of xs, that would be z. And the remainder? Well, the remainder would simply be the result of concatenating the rest of the left list, which we call zs now here, and the right list ys. So that gives us the complete implementation of concat. Now, what is its complexity? Well, we see that we will need a call of concat for each element of the left list. So complexity would be correspond to the length of the list xs. Sometimes we use in mathematics the notation with the double bars to indicate the size of something. So now that we've seen concat, let's look at reverse. How can that be implemented? Let's try by writing a standalone function. So we would have a function reverse. It takes xs, a list of arbitrary element type t, gives us back a list that's the reversal of xs. Let's start with the usual pattern match on the shape of xs. So if that list is empty, then the reversal of an empty list would give the list itself. If that list is non-empty, let's say consisting of a head element y and a tail ys, what do we do? But one thing we know is that the list will end with the element y. The first element becomes the last element. And before that, well, before that, we just have a recursive call of reverse ys. And then comes the head element y in the second list concatenated. So that would be the definition of reverse. So the next question is, given that definition, what is its complexity? Well, let's have a look. We know that concatenation is linear, takes time proportional to the size of the list on the left hand of the concatenation operator. So that list is a list that grows from 1 to the length of XS. That's for the first element that we concatenate, it would be the length of XS minus 1. So that's linear in the size of XS. And furthermore, we do one step for each element in the reverse list, because we go through each element of ys and put it at the end of the reversed list. So that gives us a factor of n for the concat times n for the reversal, where n is the size of XS. So we get quadratic complexity of reverse, which is a bit disappointing because we all know that if we have, let's say, an array or a linked list, a mutable linked list of pointers, then we all know how to reverse in linear time. We'll see later on how we might do better and get down the complexity of reverse, but for the moment we'll leave it at that. So here's an exercise. The question is, how could you write a method that removes the nth element of a list XS? If n is out of bounds in the list, then we would just return the list XS. So as an example, if we call remove at index 1 in the list of a, b, c, d, then we would expect to get back the list a, c, d. The element at index 1 would be removed. So let's grab a worksheet to see how we could answer that question. Let's write a method signature. It takes an int as an index and a list of ints, and we want to have the list that consists of all elements except the one at the index n. So how would we do that? Well, remember you have take and drop already as operations. So the easiest way to do that would be to say, well, it's XS take the first elements n, followed by XS drop n plus 1. So that means we take the first elements of the x, we skip 1, and then we take the rest of the x elements xs, which would be expressed by the expression xs drop n plus 1.